Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. This is the last lecture of session 12 about why the mean matters. In fact, this lecture is the most important lecture in the session because we will talk about how we design experiments so that we can get a specific accuracy of our estimation. More specifically, we cover only one question in this lecture, which is what should be the sample size if we want to achieve a specific accuracy of the estimated population average. Remember that we have a population, we want to estimate the average of that population. For that, we take a sample, we compute the average of that sample, and we want to have an estimate or accuracy of that estimate. So recall from previous lectures that we talked about the central limit theorem, and the central limit theorem told us that if we take the sample and we computed the sample average, then the sample average comes from a normal distribution where the average of that distribution is the population average, and the standard deviation of that distribution is the standard deviation of the population divided by the square root of the sample size. Okay, and here is the sample size. So if the sample size increases, then the denominator here will increase, which means that the standard deviation of this distribution will decrease. Okay, if it decreases, if we have a small sample, then this number will increase, which means that the distribution will be wider. Why is that important? Why the standard deviation of the distribution is important? Because if we have a distribution which is really narrow, which means that the sample size is big here, that means that most of the values of the samples, of the possible samples, will be around the center. Okay, so imagine that this curve is very narrow here, like that. Okay, so most of the values will be very close to the average, to the actual average of the population. But if the standard deviation is very large, that means that most of the value will be in a larger range around the population average. So there is a notion here of accuracy, how accurate our estimates are based on how wide the distribution will be. Okay, which means the standard deviation of the distribution. So here's an example from last time from the dataset of United Airlines flight delays, where we want to show how the standard deviation of the distribution of the sample averages will change with the sample size. As you see here, as the sample size increases, the standard deviation of the distribution will decrease. And if you notice in this curve, there are two estimates, one that is based on the simulation and one that is based on the population, the actual standard deviation of the population, which are very, very close here. Okay. Now, if I want to get a sense of the accuracy of our estimate, then we should talk about confidence intervals. Remember, we have what we call 95% confidence interval, which means that we are 95% confident that this interval will contain the actual value of the parameter, which is the average of the population. Now, when we talk about the sample average, we know that the probability distribution of the sample average is the normal distribution as we see here. So, the 95% confidence interval means that 95% of the possible averages will be within that range. From the normal distribution, we know that 95% of the values are within 2 standard deviations from the center of the distribution. Okay, so we can say that for about 95% of all samples, the sample average, the average that we will get from the sample, is within 2 standard deviations of the population average. And why is that? Because we know in advance from the central limit theorem that the distribution is normal. Okay, which means that the distribution of the sample averages is normal, which means that 95% of the samples that we can get, their averages will be within 2 standard deviations from the actual population average. Now, to compute the confidence interval, we know that for 95% of all samples, if you stand at the population average and you look 2 standard deviations to the right or 2 standard deviations to the left, you will find somewhere in that range the sample average. Okay, that's what we explained in the previous slide, that the sample average will be within 2 standard deviations from the population average, and vice versa, because the distance is symmetric. So if you got a sample and the average of the sample was located, for example, here, then you know from the central limit theorem and from the normal distribution that within 2 standard deviations from that point, to the right or to the left, the population average will be there. So the confidence interval, the interval, will capture the population average within 2 standard deviations from the sample average. So the point here is that if you start from the population average, any or not any, 95% of the sample averages will be within 2 standard deviations from it. And if you have a sample that from which you get the sample average, the population average will be within 2 standard deviations from that sample average. So each of these 2 values, the population average and the sample average, are 2 standard deviations from each other. That means that the 95% confidence interval is 2 standard deviations from the sample average in both sides. So we have 2 standard deviations from that side and 2 standard deviations from that side. So the entire interval now is 4 standard deviations around the sample average, which will be the 95% confidence interval. Why is it 95% confidence interval? Why specifically 95%? Because the normal distribution tells us that the 95% of the values are within 2 standard deviations from the average. So whatever the average that we got, the sample average we got, 2 standard deviations to the right and two standard deviations to the left is characterizing the 95% confidence interval. Okay. Now, as we said, the width of the 95% confidence interval will be 4 times the standard deviation of the sample average. Why 4? Because it's 2 from both sides. Now, the standard deviation of the sample average, as we saw last time in the previous lecture, is the population standard deviation divided by the square root of the sample size. So we can say that the width, the total width of the 95% confidence interval is equal to 4 times the population standard deviation divided by the square root of the sample size. So there is a clear relationship between the width of the 95% confidence interval and the sample size. As we increase the sample size, this value will decrease, which means that the width of the 95% confidence interval will decrease, which means the accuracy will increase, because now we are more confident in a small range about the estimated value. But if the sample size is very small, then this value will be large, which means that the total width will be large, which means that we are 95% confident in a larger interval, which means that our accuracy is not that good. Now let's apply that on a very interesting example, which is the elections example. So in this example, we have an election, and let's say that we have a candidate for which we want to estimate the voting percentage. Okay. Now we can say that the votes for the candidate are zeros and ones. Of course, the vote will be 0, means that this vote was against the candidate, and if the vote is 1, that means that it is for the candidate. And the question is, in that context, or in that scenario of the elections, can we estimate the voting percentage with specific margin of error? Okay, or of specific margin of error, or in other words, with specific width of confidence interval. Okay, so again, the scenario here is that we want to estimate how much the percentage of votes will go for a specific candidate. Okay, and we want to compute that estimate within a specific width of a confidence interval or a specific margin of error. Okay, now here we talk about voting percentage, but in the previous part of the lecture and in the previous lectures in this session, we kept talking about averages. So what is the relationship between voting percentage and averages? Let's look at our data here in this example. Our data are zeros and ones, right? Because we said that voting against is 0, voting for is 1. Now, if we want to compute the proportion of ones or the percentage of ones from this data, let's say that we have only 10 votes. So the proportion of ones here will be the number of ones divided by the total number of votes, which will be 4 divided by 10, which is 0.4. Okay, so that's the percentage of votes that will go for the candidate that we are interested in. Now, if I ask you to compute the average of these values, the average of these values will be the sum of all the values here, which will be 4, and divided by, of course, the number of them, which will be 10, which will be exactly the same value. Okay, so that means that the average, in case of the data only having zeros and ones, is actually the proportion of the ones in this data. Okay, so the average is the proportion of the ones, which means that the percentage of votes in our example. So both are the same. The proportions are actually averages, or percentages are actually averages in this example when we have zeros and ones. Okay, so if the population consists of ones and zeros, which means votes or yes or no answers to a question, then the population average is the proportion of ones in the population, and the sample average is the proportion of ones in the sample. Now remember, the 95% confidence interval is that width, which is 4 units of standard deviations from the sample average. Now, to control the width, okay, so given that we have a specific width of the 95% confidence interval, which means that I want the width of the interval to be a specific number, that number, as we saw from the previous slide, is equal to 4 times the standard deviation of the 0-1 population, divided, which is the actual population of the data, divided by the square root of the sample size. That means that the narrower the interval, the more precise your estimate, as we indicated previously. Now, suppose that you want the total width of the interval to be no more than 3%. So this is a specific example now. I want the total width of the interval to be not more than 3%. So I want the interval to be at most 3%. Okay? If that's the case, how should we choose the sample size? How should we choose the sample size? That means that the total width, which is 4 times the standard deviation of 0-1 population divided by the square root of sample size, should be less than or equal to 0.03. Okay, so that's now the relation between the width that we want and the interval, the 95% confidence interval. So that's the width of the confidence interval. We want to design the sample, which here means that we want to get a specific sample size, so that this interval, the width of that interval, should be less than or equal to 0.03. So the left hand side here is the 3%, which is the maximum total width that we want to get, and the right hand side is the formula for the total width. Now we rearrange this inequality. We get the square root of the sample size is greater than or equal to 4 times the standard deviation of the 0-1 population divided by 0.03. Now, can we directly compute the needed sample size from this inequality? Is there any unknown value here? The only unknown value here that we don't know is the standard deviation of the 0-1 population. We don't know the standard deviation of the population, right? We don't know the average of the population. That's what we wanted to actually estimate, and we don't know the standard deviation of the population. So what should we do? Let's see a demo for that, and we will get back to the slides after we see how we can get out of this situation. So let's try to simulate 0-1 population, and let's look at what the standard deviation could be for that population. So let's say that we have a population of size 10 and the number of ones here, let's say 2. So we will create an array using the ones and zeros functions of NumPy package that has 2 number of ones and 10 minus 2, which is 8 number of zeros, because remember the population size is 10. Okay, so from that we will get an array that has 2 ones and 8 zeros. Now let's compute the standard deviation for this. We will get 0.4 here. Okay, now because we don't know the standard deviation of the population in this case, we want to get a worst case. Okay, worst case here will be the maximum standard deviation. So let's try to compute multiple standard deviations for different distributions of the population here and see what could be the maximum value. So what we will do here is to try to plot a graph with the proportions of ones on the x-axis and the standard deviation on the y-axis. So we'll try to try multiple values of the number of ones, which means the distribution of ones and zeros in the population. So we will define a function, standard deviation of 0-1 population. We'll put exactly what we had here, which is the creation of the population itself, and then we return the standard deviation value of that population. Now let's create a table. We will have one column, which is the number of ones, and another column, which is the proportion of ones, which is the number of ones divided by 10. So here we will have these two columns. We didn't compute the standard deviation yet for these distributions. Remember, each row here is like one distribution, okay, because the number of zeros here is 10 minus the number of ones. So what we will do is to apply the function that we just defined here to every row in the table, specifically to the number of ones here, because the number of ones here is the parameter, and from that function we will get the standard deviation for each case, and we'll add that to the table. So now let's see the values. Let's plot the standard deviation values for every case of the 10 cases that we have here. So here, this is what we get. At the extreme cases, of course, we have 0 standard deviation because all of the values will be the same, whether they are all zeros here or all ones here. In between, we see that as we add more ones, the standard deviation will increase until it gets to this point, and then as we increase more the number of ones, which means that we decrease the number of zeros, we decrease the variability in the population, again the standard deviation will get smaller. Okay, so the top or the maximum value of the standard deviation for the 0-1 population here is clearly 0.5. Okay, even if you try a larger population, you will still get this 0.5 maximum value. You can try that on your own. Increase the number of zeros and ones here. Okay, and so instead of population of 10, you can increase that number, and you plot a larger, more higher density curve, and you will see again that the maximum is 0.5. Right. How will that help us in our computations? So let's get back to the slides. We said that the square root of the sample size, rearranged from here, will be greater than or equal to 4 times the standard deviation of the 0-1 population divided by the width that we want, which is 0.03 here. Now, if we know that the standard deviation of the 0-1 population is at most a specific value. So we can just put the worst case, which is 0.5, and then compute the sample size. So that's what we will do here. We will say that the standard deviation of 0-1 population is at most 0.5. So we substitute this by 0.5. Now we have the square root of the sample size greater than or equal to 4 times 0.5 divided by 0.03. Now the sample size is the square of this value, which is this value, which is 4,444.44. Of course, we cannot have this specific sample size. It has to be integer. So we can say that the sample size should be 4,445 or more, because of course we have this inequality here. Okay, so that means that if I want the confidence interval, the width of the confidence interval to be 3%, then I have to draw a sample of at least that size. Okay, if that number decreases, if I want the width of the confidence interval to be 1%, then of course that number will increase. We will have to have a larger sample in order to get this width of confidence interval. Remember, the width of the confidence interval indicates how accurate our estimates are. Okay, because if the confidence interval is really small, that means that we are more confident in a small range. Okay, and imagine that I told you that the percentage votes for that candidate is let's say 30%, but the confidence interval is 10% width. Okay, which means that it is between 35% and 45%. Will that be better, or I tell you that the confidence interval width is just 2%, which means that the average that I got, which is 30%, the interval will be 29% and 31%. Of course, this one will be much better. But what is the cost for that? The cost for that is that I need a larger sample to get that accuracy, or to get that confidence interval, to get that narrower confidence interval or smaller confidence interval. We'll end this lecture with 3 discussion questions that I want you to think about, and inshallah we will talk about at least 2 of them in the online session. The first one comes from a nice article, a nice online article, and I have the URL here. The article title says that poses a question: how can a poll of only, poll of course means like a sample, how can a poll of only, or voting from a sample, how can a poll of only 1,004 Americans represent 260 million people with only a 3% margin of error? Okay, just one note here. When we say 3% margin of error, that means that on each side it will be 3%. So that means that the confidence interval width is actually 6%. Okay, so that's a terminology that you need to understand here. Okay, so when I say the width of the confidence interval, so that's the total width of the confidence interval. Okay, which means if it's 95%, it will be 2 standard deviation to the right and 2 standard deviation to the left. But when I say 3% margin of error, that means that I want 3% from each side. Okay, so it will, the total width will be 6% in this case. So look at this article and try to see the why these numbers are like that. So that's the first question. The second question: a researcher is estimating a population proportion based on a random sample of size 10,000. Okay, a population proportion. Okay, so we are trying to estimate a population proportion based on a random sample of size 10,000. Now the question is, fill in the blank with a decimal number, with integer, with chance of at least 95%, the estimate will be correct to within what? Okay, within what? So I want you to compute a value here. Okay, so that will indicate the confidence interval, right? So with a chance of at least 95%, the estimate will be correct within some range. Okay, but usually when we say within, that will be one side of the range. Okay. Now the last discussion question. Let's say that I'm going to use a 68% confidence interval. So notice here that the confidence interval is different. It's not 95%. It's 68% confidence interval to estimate a population proportion. Again, I hope that you know now that a population proportion is equivalent to sample average. Okay? In case of course, 0-1 values, like votes or answers to questions, to yes/no questions. Now I want to get a total width of my interval, which is 68% confidence, to be no more than 2.5%. So I want the width to be no more than 2.5%. Now the question is, how large must my random sample be? So I will get a random sample from the population in order to estimate the population proportion. What should be the size of the random sample that I should draw from the population so that I can get this width of the interval of the 68% confidence interval. Okay, think about these questions, answer them, and we will check inshallah the answers together in the online session. With that, we end one of the most important sessions in our course. Inshallah, we will have a new session starting from next time. See you inshallah in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.